Can anybody tell me what work is? Force over distance. Perfect. That's a great definition. Force will do work when the particle undergoes displacement in the direction of force. Okay, so in other words, if you're putting a force on something and it's moving in that direction, it's doing work. If it's moving in a different direction, that force is not doing work. Okay, so work. Force through distance. Okay, in this textbook, to define work, we use U. You know, because you work. I don't know why they use U, but they do. So we use U for work and du for the change in work or a little piece of work. And work is the product of force and distance in the same direction. Okay, that means that you can have force without work. If I get on this table and push down really hard, am I doing any work? No, I'm not doing any work because the table's not moving. The force that I'm putting on the table is not going anywhere, and therefore I'm doing no work. But if I pushed on this and I moved it across the table, I just did. Our units, this is probably all review. Newton meters for SI, foot-pounds for AES. And what do we call a Newton meter? A joule. Very good. We call 1 Newton meter a joule, and we use that for work or energy. We don't use that for anything else. We don't use it for torque, even though torque is also Newton meters. We wouldn't call that a joule. But we do for work or energy. And you can see one thing that's probably coming back is the dot product. If we have this force and it's pushing on that particle, and that particle is moving along this path, notice the path is not the same direction as the force. We have to project the force onto the path, onto the tangent of the path, in order to figure out how much work is getting done. How do you do a projection? Dot product, right? So du is going to be equal to F ds cosine theta. That is the magnitude of F times the change, the small change in distance, cosine theta, and I think you can recognize that you get this out of the dot product. If we kind of change that around and we just say that's du equal to F cosine theta ds, and we take the integral of both sides, that's going to give us the work from 1 to 2, or u2 minus u1, equal to the integral from the initial position to the final position of f dotted with dr. The dot product is going to give us that cosine. Okay, f is a function of position. Or if f is a function of position, we have this equation to use. You notice there's a bunch of s's in it. If the force and displacement are in the same direction, we get positive work. If force and direction are in opposite directions, we get negative work. So in this one, the work from 1 to 2 would be positive. If force and displacement are in opposite directions, we get the work from 1 to 2 is negative. And when they're perpendicular, the work from 1 to 2 is 0. Okay, this is probably going to steer away from what you've learned, but come right back to something that's very familiar. Okay, so it's only going to steer away for this one slide. And basically what we're going to do is we're just going to do a derivation to figure out where we get the principle of work and energy. We just had the principle of impulse and momentum. Now we're finding the principle of work and energy. And we start off with Newton's second law, no shocker there. And we keep in mind that that is actually the force in the tangential direction equals mass times acceleration in the tangential direction. And we also know AT equals, or AT ds equals v dv. We recognize that this component of acceleration, the tangential component, is the one that's in that kinetic or kinematic equation. We talked about that in kinematics. That's only to the tangential component. The normal component is due to change in direction, whereas this is due to a force. So I can go ahead and solve for AT is equal to v dv ds. The only thing I did was divide by ds. And I'm just going to plug that in right here. The sum of the force in the tangential direction is equal to mass times the velocity times dv ds. I'm going to go ahead and throw the ds on the other side, and we get sum of the force in the tangential direction ds is equal to mass times velocity dv. And then, I'm sure you would have figured it out already, I'm going to integrate both sides. And we start off, this is from S1 to S2. And on the right-hand side is V1 to V2. Okay, so we end up with the sum, the integral of tangential force, ds, from S1 to S2 is equal to V squared over 2 times m from V1 to V2. So now we've got, well, what is Ft? That is the force in the tangential direction. If we're given a theta, well, that's just going to be F cosine theta, right? So we have the sum of the integral from S1 to S2 of F cosine theta equals, well, this is just 1/2 mv2 squared minus 1/2 mv1 squared. And what this is telling us is that this part is the sum of all the work done from 1 to 2. And that's going to be equal to the kinetic energy, we use a T for that, the kinetic energy 2 minus the kinetic energy 1. This can also be written as T1 plus the sum of the work from 1 to 2 is equal to T2. That is the principle of work and energy, which just basically says we start off with a certain amount of kinetic energy, we do some work, and we end up with more kinetic energy. Then there are some very special forms of work, and these are forms that create potential energy, which is something you've already learned about. The first one we're going to talk about is the work of a weight. We're going to use that same equation where the work from 1 to 2 is equal to the integral from R1 to R2 of F dot dr. If we have a weight, the force is always in the j direction. So we're just going to say force is equal to negative W times j. That's what's defining it as a weight. Gravity always pulls straight downwards. And then we have to figure out dr. Well, dr is a vector, and it's going to be made up of a little piece of x times the I plus a little piece of y times the j plus a little piece of z times the k. Okay, and what is that dr? It's just the position vector in the direction of the path. And you can see the little dr right here pointing away from the particle in the direction of the path, so the tangential direction from the particle. Okay, so now we got to do the dot product. That's pretty easy. We'll have negative Wj dotted with dxi plus dyj plus dzk. That's this dot product right here. So you multiply the two i's together, you add it to the two j's multiplied together, you add it to the two k's multiplied together, right? So we would end up with 0 times dx. So we'd have 0 dx minus w dy plus 0 dz. Now the 0 times dx, those obviously are 0, 0, and 0, and we just end up with negative w dy. Okay? I have done nothing in here except generalize the fact that the force acting on it is always in the y direction. It's the only thing. So this could be for any weight whatsoever. And that is what we have to replace this with. So we would say the work from 1 to 2 is therefore equal to the integral from y1 to y2 of negative w dy. Well, the weight's not changing, so I can take that out of the integral sign. So that's just going to be equal to negative w times y2 minus y1, which is negative w delta y. Okay, this is a very important derivation that I think you guys already knew. And it tells us the work of a weight is independent of path. How do I know it tells me that? Well, because look at how I calculated it. I put in a y2 and I put in a y1. If I have a y1.5 in there, it doesn't matter where y1.5 is, because it's not in my equation. If I take the stapler and I lift it from here to here, and then I go from here back to where I was, how much work have I done? 0, exactly. It's path independent. It only depends where you start and where you end. Okay, so I can do whatever I want. If I end in the same place, I've done no work. Is that new? Okay, didn't think so. All right, work of a spring, same idea. We're going to have f dotted with dr, and we're going to have the integral from r1 to r2. The force of a spring, in this case, we're going to say the force of the spring is in the I direction. And if my dr is also in the I direction, then I can say the work from 1 to 2 is the integral from r1 to r2, or I'm changing it to s because we're assuming the path is along the spring. So we're going from s1 to s2, and we're doing negative fs ds. And that just comes from the dot product, because I have two things in the I, I have nothing in the j, nothing in the k. What is the force of a spring? K delta s, good. So I'm going to just plug that in for force of the spring. So we have the work from 1 to 2 is equal to the integral from s1 to s2, negative ks ds, and I integrate. I get negative k s squared over 2 from s2 to from s1 to s2. So the work is going to be equal to negative 1/2 k s2 squared minus 1/2 k s1 squared. Spring and a weight both have path-independent energies. Right? So basically, if I take a spring and I move it all around, it doesn't matter what I do. If I go back to the same space, I have done 0 work. Same thing with a weight. If I move it up and down and all around, if I move back to where it was, I've done 0 work. Because the equations only have the beginning and ending position and nothing else. What we call these are conservative forces. And basically what that means is the amount of work done is independent of path. The way that we write this is just the integral over a circular path, pretty cool little symbol, the integral over a circular path of f dot dr equals 0. Another way to say it is work is conserved. And then energy. We need to define the term energy. And this is defined as the capacity to do work. Okay, it's as simple as that. Energy gives us the capacity to do work. So, if we are independent of path, and I pick up the stapler and move it up, I've given it more capacity to do work. Potential energy. Potential energy is the capacity to do work. So for potential energy, for gravity, we're always going to say that the work from 1 to 2 is equal to negative W, the weight, that W stands for weight, not work, times y2 minus y1. If we make the assumption that we have some datum that we're going to put right here, and we have to pick that datum, we're going to pick some datum of having 0 potential energy. That's going to make our y1 0. And then we can say potential energy, which they use a V for. Yeah, I know. Potential energy of gravity is just going to be equal to Wy. They use a V for potential. Potential, I don't know. So what that means is if we go up, we are adding potential. If we go down, we are subtracting potential. Notice that that is the opposite of work. If we go up, we're doing work. If we go down, we're not doing work. So our potential energy is the opposite of work. For a spring, we have a very similar thing. U1 to 2 is equal to 1/2 ks2 squared minus 1/2 ks1 squared. And we're going to throw in a very, very, very big assumption that you have to remember that we threw in. This is a big assumption. The unstretched position is s equals 0. Okay? That means that for each and every problem you use potential energy of a spring on, you have to set up your S equals 0 to be the unstretched position. The S that we have in this equation is really a delta S from the unstretched position. Don't forget about that, otherwise you'll just plug in S's and think you're getting the energy. It's only S from the unstretched position. And then our potential energy of elasticity is 1/2 K S squared, because we're putting in a 0 for our S1. Notice that we can't have a negative potential for spring. If we start with our 0 potential at the unstretched length, if we stretch it this way, we get positive potential. If we stretch it this way, we get positive potential. There's no such thing as negative potential energy for a spring. So basically what that leads us to is this equation that we derived. The equation says initial kinetic energy plus the potential, or plus the work done from 1 to 2 equals final kinetic energy. This term should actually be separated out into two terms, conservative and non-conservative forces. So we can say T1 plus the work from 1 to 2 of conservative forces plus the work from 1 to 2 of non-conservative equals T2. Then all we're going to do is say, well, these conservative forces are path independent. That's the definition of a conservative force, is it's path independent. And if it's path independent, we can just figure out where it is at the beginning and where it is at the end and measure its potential energy. But remember, I said the potential was the opposite of work. So the sum of all the work from 1 to 2 of conservative forces would be equal to the opposite of the change in potential, V2 minus V1. So just distributing that negative sign, I get the sum of work from 1 to 2 of conservative forces equals V1 minus V2. I plug that back into my equation, and I end up with initial kinetic plus initial potential plus the sum of work from 1 to 2 of non-conservative equals T2 plus V2. The book kind of makes a big deal. If you're reading through the textbook, they make a big deal about moving between these two equations. But they're the same equation. I don't really even understand why the book likes to present the first equation and have you use it a whole bunch, and then later present this equation. Because this equation is the same equation. The only difference is we brought in potential energy, so we broke up the work. Okay? So I suggest get familiar with this equation. It's what you're going to use in every single problem. So let's do some example problems. So this one states we're given that the weight is 50 pounds. We're given that there's a force applied, and that force has an equation. So I'm going to start doing those. We've got weight of the block is 50 pounds. The force is 40 plus S squared pounds. So the force is changing with distance. And we're given that mu k is equal to 0.2. And we're supposed to find the velocity when S equals 1.5 feet. Okay, so what do? I'm going to need a free body diagram. Draw a free body diagram. So we know everything that's acting on the block. We got the weight pushing down. We got a force of the spring. We got the normal force. Got F. And we've got our friction. Friction is going to try to keep the block from moving, so our friction is going to look like that. And I'm going to put F sub F because we already have another F. That's the force of friction. We could jump into our normal kinetics if we wanted, and we could solve the problem that way. But it would be sum of the forces equals mass times acceleration, and it's asking us to find velocity. So we'd have to go back and from acceleration find velocity. It would be a very good, valid way to solve it. There's nothing wrong with solving it that way. But work and energy is kind of a shortcut. So our equation was initial kinetic plus initial potential plus the sum of the non-conservative work from 1 to 2 equals T2 plus V2. What is our initial kinetic energy? 0. We're not moving, so it's 0. What's our initial potential energy? Yeah, as long as the spring is unstretched and we're setting our datum for potential to be right in the center of that block, then it's also 0. What is going to be our non-conservative force? Friction. Good. Friction is a non-conservative force. What else? The force. Yeah, friction and the force are both non-conservative. Right? The normal force would also be non-conservative. But do we take that into account? No, why not? It's perpendicular to our path. Right? The normal force is perpendicular to our path, so it's doing 0 work. Okay? So we're going to say, well, we need to take the integral from R1 to R2 of F dotted with dr. That's for our force. And then because friction is pointed in the negative direction, we're going to say minus the integral from R1 to R2 of frictional force dotted with dr. That's going to be our two non-conservative forces. We're not going to bring in the spring force, and we're not going to bring in the weight force because both of those are conservative. And they come in with potential energy. And that's going to be equal to, what's our final kinetic energy? 1/2 mv squared. I'm putting V2 just so we know it's the velocity after. And then I have to do our final potential energy. What's going to be our final potential energy? 1/2 ks squared. Okay, now we got to do a little bit of work on this one because we have to figure out, and I'm out of time, but we're going to have to figure out what our normal force is. And we can figure out what our normal force is just by doing sum of the forces in the y direction equals mass times acceleration in the y. We know it's not accelerating in the y, so therefore we're going to have F sine 30, which is the y component of our force, plus 50 pounds, negative F sine 30 minus 50 pounds plus NB equals 0. That's the sum of the forces in the y direction equals 0. Then we can solve for our normal force. Once we have that, we set up our normal force being equal to, our frictional force being equal to mu k n. We put all the information in here. Solve for V. Any questions about that? Are you confident you could get to the end of this problem? Some of you? Okay, good. Well, hopefully that was a good introduction.